Welcome. Just a few quick announcements. We have a reading group going on, which I will probably formally announce this week once we're done. We're currently reading the Destructor paper. If you care about high performance concurrency patterns, come out. Read the paper as well. It's really short, really accessible. One of the things that's been kind of requested over and over again, but I haven't quite come up with how to do it, is people want to hack on various things. So if anyone cares about hacking on whatever, I'm looking for a hack night organizer. It's not a lot of work. It's maybe setting up a venue, making it regular, and then it just gets auto-announced on the meetup. So if anyone's interested in like a regular coding session once a month or something like that, or wants to help facilitate that, please come talk to me. DevOps Days, October 25th and 26th. It's a DevOps conference. It is part structured, part unconference. They're looking for submissions. They have a few and they like more. If you have a submission in mind, or if you're curious about what a submission would entail, please come up and talk to me and I'll point you in the right direction. And we've got a few meetups already scheduled, so they're around type classes, and one's around Linux performance by Brendan. I'm looking for you.
Leg.
Sir.
Leg, I think.
I can't.
Like break a leg.
And okay, most of all, I'd like to thank, and so I'd like to thank Hootsuite for making this happen, and I'd like to thank Peter for volunteering to do this.
Thanks. Okay, this is a little suspicious. Thank you. My name is Peter Geoghegan. I work for Geoghegan. A little bit of background information. Today, mostly worked on performance improvement, performance features, group commit, things of this nature. Also, worked on pgstat statements, which some of you may be aware is a module that Postgres makes available for instrumenting query execution costs. So, for example, it'll show you the aggregate duration of a particular query and the other associated costs of executing that query against your production database. So I work for Heroku on their database as a service offering. Also, I'm at Postgres on the day job as well, so a lot of different responsibilities there. What's the talk about? What are you all here for? I'm going to talk about more things than I probably should in an hour. It's not terribly sensible for me to do this, but I'll do it anyway. Aspects of concurrency like locking, transaction isolation, MVCC, which is the concurrency model that Postgres uses, how that compares to others. It's mostly how the database handles things so you don't have to, and how Postgres fits into the wider landscape. Slide. Okay, two-phase locking. What's two-phase locking? Well, it's something that Postgres doesn't use, but serves as an interesting basis of comparison, perhaps. Slide. Okay, so it's the traditional concurrency model that databases have been using since the 1970s and many still do. Most prominently, perhaps, SQL Server and IBM DB2. Technically, they use strict serializable two-phase locking. So this is a classic model from the 1970s, initially pioneered by IBM SystemR, as in fact are many database, SystemR was an incredibly influential database system developed by IBM in the 1970s. However, I am a Postgres guy, always have been, never worked with another database in any capacity. So two-phase locking seems really weird to me. Because two-phase locking data, in a sense, becomes sullied, as I've started here, simply by virtue of someone else having seen the data. So, in other words, a transaction will block on another transaction because some of the a write will block because some of the rows have simply been observed by another transaction. To my mind, this is kind of weird, but it is in fact in some sense, the standard, the traditional model. And if you think about it, this makes a certain amount of sense. And big banks love this, or very conservative organizations, because it's very easy to reason about. Things do happen in a concurrent order. However, it's a model that's fallen out of favor, particularly in the last 15 years. Sorry, do you have a question? No? Okay. Slide. Okay, so this is the model of PostgreSQL, multi-version concurrency control. So I guess this picture is supposed to illustrate that concept. Next slide. Okay. Popular, influential. You've got Postgres, Oracle, many other systems. So the concept here is that multiple versions of any given row are stored at the same time, and different sessions will have inconsistent ideas as to what the contents of different tables are. They see things according to their current snapshot, as opposed to, if you do an update, updates are not in place. Rather, you create a new row version, and then the old row version becomes invisible to your transaction, and yet may well still be visible to another. There are still locks involved in order to ensure correct behavior, but there's a lot less of them. They're a lot lighter weight than with two-phase logging. Slide. A little bit here about logging in non-traditional databases and how Postgres fits into the wider landscape. I somewhat casually follow development of other database systems, so I'm just noting here that a lot of progress, a lot of the major features that MongoDB has, involve our logging is, far more granular than it was in the last release. So there's better concurrency for writes. So they in 2.2 they removed the spill write lock, and now they have a per database write lock, and they want to have collection write locks next, which is collection is roughly analogous to a table. On the other hand, if you look at some of the new SQL databases, one in particular I think is an interesting model, not necessarily at all in competition with Postgres, is a thing called Vault TV, where we only have one big session so in fact it completely eliminates concurrency. That is to say, any given, there can only be one session at a time. Now, there could be concurrency in the sense that they have parallel query. In fact, I would consider that to be essential given their architecture, but only one session can execute at any given point in time. Slide. So they sort of eschew all of these different database concepts like buffer manager, write-ahead lock, crash safety, and require you to interact with the database entirely by calling stored procedures written in Java. Now, the stored procedures do use SQL, so it is a relational database. So it is, a radically different approach to traditional databases. If you can accept the very particular set of trade-offs that it presents, if you can plan for those, plan for limitations of Vault DB, that you don't have very, very small transactions, that everything needs to fit in memory all the time. You can't do DDL, so you can't add a column to a table without taking the whole system down, because those require locks. But it's an interesting model, and I thought I'd just cover it passing as a basis of comparison, perhaps. Slide. Here is Dr. Michael Stonebreaker, who in recent years has worked on Vault DB in the commercial sector, but was the sort of charge of the group at Berkeley that originally developed Postgres. So I've sort of casually followed his career. Slide. Okay, now get down to the details. Blocking, table level locks. So Postgres frequently takes locks implicitly, automatically without you necessarily being aware of it. And typically these locks will last only the duration of the transaction. So you can explicitly lock, for example, tables using a lock command in SQL, but you cannot explicitly unlock because generally you'll want the locks to persist for the duration of the transaction. This link here will give you a sort of summary of all possible locks in Postgres, and it includes a useful conflict table so you can see how different locks conflict with each other and indeed when and where they are required. I'm going to go into the details now. I'm just going to cover the concepts in sort of broad strokes. And some of these lock themselves, and some don't, and then so they have different sort of properties in terms of where they're used and if they block each other and things like that. So, slide. Now these locks are viewable within the PG locks system view. You can join this against the PG stat activity system view, get a sense of why the locks were required. I've got a couple of links here to the Postgres wiki, which has some example queries for usefully breaking down relatively low level information. I haven't included that here because they're, in the first instance, the sort of blocking problems, lock monitoring page there, those queries are quite verbose, and the lock dependency information queries, which are recursive, are kind of an abomination. Really huge and gnarly, and you probably don't want to think about the exact details too much, but you can use those and you'll be able to see if you've got a locking problem in your database, if something is locking up, you'll be able to use these queries to, for example, isolate what session is it that's the real offender, because bear in mind that locks can be transitive, and it can be the case that you're blocking on someone that's blocking on someone that's blocking on someone. You want to know who the real offender is, as it were. So, just to give you a few examples, blocks automatically taken on inserted rows, or a row when it's updated or deleted. Unique constraints, kind of a special case because they're enforced by, so if you insert, say, the value 5 into a table, and some other session has already inserted that value but hasn't committed yet, your session is going to block pending the completion of the other transaction because it's not clear whether or not you need to have a unique constraint violation yet. So they're kind of a special and interesting case in that regard. Slide. There are other locks involved in the implementation of the database. So the example I cite here, although there are many, is the B-tree code, B-tree index code, which is sort of the index type that you're going to want to be used. Most of the indexes you'll have in Postgres will be B-tree indexes. If you declare a primary key or a unique constraint under the hood, that is a B-tree index. So this code uses a technique called latching to ensure concurrent access is correct. You don't see, the session doesn't see any consistent view. This is actually totally orthogonal to table level locks. I only mention this really because people tend to confuse the two, so it's worth being aware of that distinction. Slide. Okay, so let's talk about transaction isolation. Postgres provides a number of different levels of transaction isolation. These can be controlled by changing setting within PostgreSQL.com, or even can be changed, per session if that's what you require. You may not want to use the same transaction isolation level all the time, and so on and so forth. So what is a transaction isolation level? So in general, Postgres is supposed to let you pretend that your transaction is the only one operating. Essentially, one of its main jobs can be reduced to that. So you can pretend that your transaction is the only one. This is also the job of locks, and they were pretty much the same in all isolation levels. So transaction isolation describes essentially the degree to which this illusion is convincing. What you see and what you don't see. So a lot of people aren't particularly aware of this. They have no idea, and they mostly get away with that. But it's certainly worth being aware of these concepts, particularly if you have a very important business application, dealing with financial data, things like that. And some people will always use the higher levels of production, others won't. Slide. Okay, so the default level that you'll automatically be using. Incidentally, with Postgres, we're always operating in the context of a transaction, if perhaps implicitly. We cannot not be in a transaction. It's not possible. Okay, so recommitted is fine for many purposes. Each statement executes these rows that are consistent with its snapshot. Each statement gets a new snapshot. So there's no danger of your select statement seeing an inconsistent view, but within a transaction, multiple select statements will perhaps see an inconsistent view because some other transaction will commit, and thus you'll see the committed data from the other transaction. So you can have anomalies where you read something twice and it's different the second time, things like that. So there's different ones called non-readable reads and phantom reads. I'm not going to go into the details of what they are, but essentially it's that another transaction commits, you see what it commits rather than the state of affairs prior to it committing. You never see so-called dirty data, which is data that another transaction has written that has yet to commit or that subsequently aborts. So obviously a transaction can still see the changes it makes, but that doesn't count as dirty data. Slide. Okay, now I'm going to talk about the next level up in Postgres in particular, repeatable read. A level up from recommitted. What the behavior you used to get currently the behavior you get at repeatable read level was the behavior that you got when you asked for serializable level in previous Postgres releases, and that's because in 9.1 there was a new, better serializable level, and I'll describe that in a moment. So Oracle implements something just the same, except it continues to call it serializable. It doesn't have the thing that Postgres got in 9.1. It's kind of similar to recommitted, except that you have you don't have one snapshot per statement. Rather, you've got one snapshot per transaction, taking at the start of the transaction. And you're going to have a consistent view throughout the duration of the transaction. But apart from that, there is one big downside or difference, which is that in order to ensure that certain anomalies don't occur, Postgres has a license to throw a serialization failure. So you basically have to be prepared for your app to randomly have an error, handle that, and potentially restart the transaction from scratch. So that is a burden that places on you. This can happen if, for example, you update the same row as another transaction, and then you're blocking on the other transaction, and the other transaction goes and commits, and you'll get a serialization failure you have to deal with.
So Peter, how do you deal with that?
Well, you have to code it in your app. You have to be explicitly aware that can happen and potentially be prepared to start from scratch.
Retry, yeah.
Yeah.
How would you test for something like that?
Pardon?
How would you reproduce data to test for something like this? Is it possible?
Well, I mean, it happens predictably in the sense that it's predictable that if another session does, for example, updates a certain row, if you go to update that same row, and then the other transaction commits, the one that originally updated the row, then you will have a serialization failure. You just need to generally be concerned about that. You can't really test for it in any sense.
So it's just competing commits.
Essentially, you could say that, yes. But I mean, of course, it only matters if the other session does it at the same time. So, you had a question? Yeah.
So is this called optimistic blockchain?
Yes. Yeah, you can describe it as optimistic. So anyway, it's only an issue when you don't have to worry about it if you have a transaction that isn't going to write anything. That won't have a serialization failure. So the really compelling case in my mind, at least, is for reporting. And this is where the distinction becomes quite important between people read and read committed. Consider, for example, a typical kind of report you might want to produce for a business application, something like that. Financial report. It's a document describing whatever it might be. I suppose it's some kind of summarization of sales, say at the department granularity or something like that. And then at the end you have a total for for all departments, something like that. If you were to write that such that there was two distinct queries and you were using read committed, if that data was changing all the time, potentially another transaction from the reporting transaction could commit, and then you would see an inconsistent state to be a race, and potentially the numbers wouldn't even add up, which could, yep.
This is all for multiple queries in a transaction, not for one.
That's exactly right, yes. You don't have to worry about it if it's for one query, but for multiple transactions, this can happen.
Queries in a transaction?
Yes, multiple queries, for multiple queries in a transaction, this is possible. You will never see an inconsistent state for one query because one query has its own snapshot at recommitted level. And people read, as I said, only has one transaction, one snapshot per transaction, and thus you would always see the same row versions unless you yourself within the transaction change them. Slide. Brief aside, white skew anomalies. So far, I've described two of the transaction isolation levels. I'm going to describe a third one. The one I mentioned was new in line 1, but I'm going to have to give you a certain amount of context first. In order to give you that, I'm going to describe right skew anomalies. Even though the way the SQL standard describes the isolation levels, even though that's correctly implemented by, say, Oracle serializable level or people read in Postgres, there can still be anomalies. Slide. So, is it really serializable? What does that mean? Well, quite simply, is it as if the transactions were really on their own? Is it like as if there was a serial ordering of the transactions? Can we assume that, blocking aside or serialization failures aside, that it's really as if your transaction was the only one? Slide. And the answer is no. Surprisingly, because if it was yes, then. So the answer is no. There are a number of different types of anomalies that can occur that are very similar, but I'm describing right skew anomalies that an obvious, relatively easy to understand one. They're all essentially, quite similar. Incidentally, not that many people know about this stuff, which is kind of surprising because if you're doing financial reporting, you can get like wrong answers. So, that could be a problem. Slide. So recall that with MVCC, readers don't block writers, writers don't block readers. This is really cool. This is really useful. And it is pretty much the dominant model. Remember also that I said that banks like two-page logging databases, like DB2. They like them because they're simple, they're easy to reason about, easy to understand. It's a very simple model when you think about it. It can have right skew anomalies because readers do block writers. Writers do block readers, unlike with Postgres. Slide. So, what is a right skew? So it turns out that the two-phase locking system, like IBM DB2 or whatever, might not be that dumb for doing this. You'll recall I said they consider the data to be sullied by having been seen by another transaction. Is that a reasonable position? Well, usually not. But sometimes it does matter. And it will matter to you someday, probably, at least if you're the kind of person that showed up to this talk. Slide. So I'm going to give you an example of a right skew anomaly because that's really the simplest way of illustrating the problem. This is taken from Wikipedia snapshot isolation article. So consider the example of a person with two bank accounts in the same bank might let the person have a negative balance in aggregate. One of the balances is enough that invariant is maintained. So you code this up in a pretty obvious way. You check what the balance is in both accounts. You go to update one, and then you commit. Or if that's not possible, if the invariant if it can't be maintained because they don't have enough to to respect that, then you throw an error. Seems kind of obvious that ought to work, but it may not. What if two requests come in at approximately the same time? Slide. You get a skew. So here we see transaction 1, transaction 2, each take a snapshot. I'm assuming this is repeatable read or serializable in Oracle. So they do pretty much the same thing here. Number one, check this one here. They check the balance of each of the accounts, and then one of them deducts from account 2, and the other one deducts from account 1. Because remember, they will have a view of the database at the start of the transaction when they acquire the snapshot. So they don't, in effect, know about each other. So what happens? Then it's not going to be the case that the aggregate balance will be negative and big problems, presumably, for overall the application. Slide. Is that clear to everyone? Is that example useful? So this only occurred because there were two bank accounts, and there was lots of implicitly applied by those update statements for the account balance for each account might have a balance in an accounts table or something like that. I suppose if it was like the one table, the one bank account, of course it would have worked because the update statement would have required the update statement would have required a lock, and then you would have had serialization failure. But that didn't happen because there was two rows, right? And one updated the other. That's kind of the concept of the skew. That's where the skew bit comes from, if you like. So what do? Do you accept this as a trade-off that you've got to make? Or do you artificially introduce a white dependency in this scenario? Well, you could hack around the problem by doing that, but then you might even not know about the problem. This stuff could be pretty slow. So what do? Well, you use serializable in Postgres 9.1 Plus. Because in that version, serializable is implemented as something called serializable snapshot isolation, SSI, and you get true serializability. So you in fact maintain many of the advantages of MVCC, and yet still have the advantages of two-phase locking systems. You're guaranteed a strict serial ordering of transactions, or rather, the way you observe things is consistent with some strict ordering of transactions. Slide. So this is, talking about serializability, serializable snapshot isolation. This is recent research. So the guy's PhD thesis in Australia in 2008. We went and implemented it with the first. It's much better than two-phase locking. It's not like you're just having a serialization failure because you're not having a serialization failure rather than just blocking. So it's not equivalent to two-phase locking. It's actually much better because what Postgres is actually doing is it's giving you something very similar to repeatable read isolation level, except it is maintaining internally a list of or a structure that contains read-write dependencies. So in fact, serialization failures will happen, but they'll happen much less frequently than blocking would happen with a two-phase locking system. So it's equivalent to some serial execution order, doesn't promise you which one. Now the great thing about this is if you've got a huge sort of sprawling application, you've got a lot of developers, maybe they don't appreciate these issues that well, then provided you're willing to deal with the serialization issues, you can be sure this stuff won't come up. I'm sorry, provided you're willing to deal with serialization failures, like I meant to say, this stuff doesn't present any issues for you whatsoever. You can be sure it will work just as well with many sessions as with one. Slide. Race conditions. I'm going to talk a bit about race conditions. I sort of already have been, but I'm going to talk about one other type of race condition. Slide. These occur when there's a sort of a tacit assumption that things are happening in a certain order. The right skew anomaly is an example of one. The big offender that I see time and again is a trigger that enforces a business rule. In other words, you insert into a row or something like that, and then after trigger fires, it selects something else, it checks some other condition, potentially throwing an error if some business rule is not respected. But this is kind of broken unless you're using serializable isolation level. There are reasons why you might not want to use serializable isolation level. The overhead is greater than other isolation levels, but if you were, it wouldn't be a problem. Slide. So the advice here is to try and avoid it. It is sort of a problematic pattern. So if possible, avoid it entirely. It's also possible for you to block the entire table, expose at the SQL level. You can do a lock table. That'll prevent people from writing to it, but not reading from it, by default anyway. But there are some better options as well. You can use a determinative constraint, for example. Postgres has something called exclusion constraints, which allow you to, for example, one way of describing it is solving the double bugging problem. So we're sitting here in this room, we're using this facility. If someone was organizing that, the allocation of rooms or something like that, they couldn't very well have two sessions occurring at the same time, because of course we're using this room right now. So with exclusion constraints, there's a derivative construct that allows you to prevent that from occurring and to do so quite efficiently. So you can they've been described as a generalization of unique indexes. So rather than a unique index where you can only have one session, or sorry, you don't have like strict equality, you can have exclusion constraints on arbitrary other operators, such as overlapping. So you can have a sort of a column representing the period in which the room is occupied, and then if anyone inserts and that constraint is violated, then it's impossible to violate that constraint, and it works very well. It's really much better than using to sort of trigger hacking. Well, you can, as I said, you can always use SSI. That might be preferable. SSI will, like I said, it's equivalent to a strict serial order of execution of transactions. Slide. Talking about deadlocks, they happen. Slide. What's a deadlock? Well, I'm sure many of you know that a deadlock is when you have this sort of mutual dependency between two transactions. One is waiting on one lock that the other holds, and the other one is waiting on one lock that the first one holds. So it's a deadly embrace. They cannot proceed. Something has to happen. And what happens is, after deadlock timeout number of seconds, that's a parameter, the deadlock detector in Postgres kicks in, examines the dependency of the lock dependencies in the shared lock table, and determines that there's a deadlock. Before it even checks, 1 second has to pass, because it wouldn't be efficient if it was more eager than that usually. So when 1 second passes, the deadlock detector kicks in, randomly aborts one of the transactions, and then the other one can proceed. So this is obviously something we would prefer not to happen at all. And the key to avoiding this situation is to acquire locks, including implicit locks from updates or from enforcement of foreign keys, things like that. And to acquire all these locks in a consistent order is how we can prevent these sorts of deadlocking scenarios. You'd have to do that sort of analysis on sort of case-by-case basis, so it's hard to give much general advice beyond that. But Postgres will, of course, at least not prevent you from, the sessions from just hanging forever. It's aware of these issues. Slide.
Peter, how frequently do you actually see deadlocks at Heroku? Something Heroku scale, how frequent is it?
Probably pretty frequently. A lot of the time, people will, I suppose with Heroku, it's not super clear where our responsibilities start and end. So it depends on the individual situation. But yeah, this is something you see an awful lot in certain types of applications. That one pattern I've seen before is people explicitly locking rows and then keeping that lock held for a very long time. In general, long-running transactions in Postgres are a bad thing because in the case of serializable or people read transactions, they prevent vacuum, the garbage collection process from running, because it will only do that for rows that aren't visible to any session. But more importantly, perhaps, those transactions will continue to hold their locks. So if you have like an idle transaction that's running, then you've got all these locks held, they potentially blocking other things. That could be quite a bad scenario to have those locks held indefinitely. Does anyone have any questions?
Idle and transaction, when you look at the process list, can you see that? Is that what you're talking about?
Yes, you can. If you look at the PG stat activity view, that will give you a status for each transaction. So you'll be able to spot idle transactions there, and it'll also show you when the transaction started. So you could easily write a query to say, okay, show me all of the sessions, what they're doing, that are older than, where the transaction is longer than, say, 10 minutes. So there is an expense associated with long-running transactions that we probably need to be conscientious of. Okay.
Vincent?
Pardon?
Do you see the deadlock checker triggering more often under higher levels of currency, like more parallel queries going on?
Well, it would stand to reason that there would be some correlation, but there's no reason why applications, must necessarily have deadlocks. Many applications will never have deadlocks. It might be that you, as an application developer or DBA, become aware of deadlocking going on and optimize the problem, if and when it becomes an issue. So I suppose, if you've got more things running, then you've got more things that could be locked. Or equally, if you have, say, one table that has one row, and you have like this sort of pattern where that's like the one setting, that different sessions can set that one setting. If every transaction is doing that, then every transaction is acquiring a lock on that row, and then you just made all of your transactions occur not in an equivalent to serializable order, but in an actually serializable order, and that's really bad.
So what about people using the array type as sort of an event source, putting lots and lots of things in a single row array?
Okay.
Do you think that sort of usage would lead to higher probability of deadlocks? And
I suppose it would, but then, if you've got a transaction that's not running for very long, as would be typical for web applications, I suppose, then that might be homework password. I knew that was going to happen. That might be an issue. But I don't think it would be a major concern, provided the transactions didn't last that long.
Yeah.
And those kinds of constructs are very efficient within Postgres because of its extensible indexing infrastructure that, for example, allows you to, very efficiently write queries that say, show me all the rows in this table that have, within that array column, the value 5. So there's a lot of advantages to those sorts of techniques. They do serve a lot of purposes, but I suppose anything can be misused. It's a good question, though. So, improvements in 9.3. 9.3 is a release set on Monday. You should check it out. A lot of cool features, but given that this is a concurrency talk, I'm going to talk about the concurrency feature. So in Postgres, foreign keys are implemented internally as triggers. They acquire locks on referenced or referencing rows. This works a lot better in 9.3. And just in general, if you do something that causes foreign key enforcement, such as inserting into a table, updating a row, or something like that, then everything you do subsequent to that in the transaction is predicated on the reference row continuing to stick around. So you think that it's entirely necessary for these locks to be acquired by foreign keys. These use something called dirty snapshot similing. About foreign key, about business rules being enforced by triggers don't quite apply because they're kind of special triggers. So you could potentially use those if you were some kind of mad person. The recommended slide. So, what is the new thing about foreign keys? Slide. They've become, in terms of the locks they acquire, in order to ensure correct behavior, in 9.3, they're an awful lot more granular. So it's kind of I described the MongoDB thing earlier on. The sort of a broad trend has been that we, make the locks that we need to acquire more granular, as Postgres progresses from release to release. And this is a prime example of that. This has been a huge feature. An awful lot of work has gone into this over more than one release. It's actually took about 2 years to implement this, all told on off. What actually happens when sometimes you can actually see the SQL executed by foreign key enforcement. If, for example, you have a deadlock, it'll show you, the foreign key query executed by the foreign key, and you'll probably think, what the hell is that? I've never seen that query before, but that's actually what it is. And you'll see something like a select for share in earlier versions, and used to be select for update in like 8.0 a while ago now. So this is, like I said, all needed for correct behavior. It's entirely necessary and appropriate for this locking to occur. Slide. Question. Do updates really prevent rows from continuing to be around in any real sense? The answer is often no. You can update every single column row. You might consider that a whole new row. That would make sense because it's different referenced value. But in fact, mostly you're not updating the key, are you? You're mostly updating everything else. Or, typically, that is mostly unnecessary, it turns out. So more granular locking introduced is expected to improve concurrent behavior by quite a bit. Slide. So the relevant triggers, which you can see, they now use this 4-node key update and 4-key share thing. You can even use these yourself in SQL if you're so inclined. It's greatly improves performance of many clients because they'll block each other far less frequently in practice. This is a very important property of a database that it has good performance with a lot of concurrent activity. Slide. So this is just showing you the SQL involved. So this is for update, an old version, for share up until 9.2. Foreign keys use these. And then you've got these two here. This is what foreign keys use, and updates will often only require 4-node key update locks, which won't block foreign keys, which is what you want. Slide. Upstart. I guess most people know what upstart is, right? Okay.
Assume we don't. Explain to us.
Okay. Well, okay. So what isn't, or what is upstart? Upstart is the ability, or this is my definition anyway, others might differ. It's the ability for someone to write a simple query that will either insert a row, or in the event of a duplicate, will update the row instead, as an atomic operation that is guaranteed to have either one of those two outcomes. MySQL has insert on duplicate key update. Postgres, on the other hand, requires you to use subtransactions in a loop, and it's rather subtle how to get those details right. There is an example of this in a few slides, but I'm not going to talk about that just yet. It's kind of foreshadowing. A lot of people want this and have for some time. Slide. I'm working on it. It is something that I'm literally working on right now. Last Friday I posted a patch, insert on duplicate key ignore. I'm going to add a insert on duplicate key lock for update variant probably very soon. How do you use this for an upstart? Well, I'll show you. You can compose it using something called a writable common table expression, or also known as a with query. I'll show you what that is in a moment. And you can get a very sort of flexible upstart that is, not only equivalent to, but in fact more flexible than the MySQL syntax that pretty much just does the right thing. So you don't have to give it too much thought, which is what we're looking for here. And in particular, you don't have to use subtransactions, which you don't have a sub-transaction entry for every single row you're inserting. That can be an overhead that is totally prohibited. Slide. What is a writable CTE? So, most relational databases support CTEs, common table expressions, with queries. This is this idea of defining a temporary table, but not a very temporary table, one that persists only for the duration of the current transaction. You can sort of use these to compose queries in a nice sort of way. You have like intermediary states, you might call it, within one of these sort of very temporary tables. You can also be recursive, and you can do all kinds of cool tricks with them, like walking trees. If they're recursive, you can walk trees and do things like that. But anyway, Postgres is unique in that it supports writable common table expressions or common table expressions as part of a write statement. So this is a writable common table expression. It's called R, and it's on an update. So if you couldn't have the fact that this is a write statement in the CTE and the fact that this under here is in the select either, both of those two things are kind of weird to people that don't use Postgres, but it's kind of cool. So anyway, what's this doing? This, by the way, this is 9.4 material, so you're going to have to wait for 2014 for this at the earliest, I'm afraid. And that's assuming I get it in. So what we're doing here is we're inserting two tuples into this table test and specifying the key block for update. Now, why does it even make sense to put a writable CT, have a writable CT? In other words, write statements don't generally have anything for you to select. So, what do I mean by that? What I mean is, you can have this returning star, forget about the rejects, returning star construct, and then you can have write statements return some of the things that were actually inserted. Potentially, you could see if you had like a serial column with a sequence, potentially see what the actual value of that ended up being at insertion time, and do something else with that. But here, what I'm doing is I'm returning the rejects from the insert statement, and the update here is updating the same table and referencing this CTE R, so potentially, if all of the inserts are successful, then the update won't do anything. If none of them are, then it'll do both of them, and then potentially you could do just one of them, depending on what's already there. So, yeah, so I'm kind of composing these sort of different SQL level features in an interesting way. This is sort of a flexible approach in that potentially this might not be an update statement at all, it might be a delete statement, for example, if that happened to make sense for your application or for your purpose. Slide? That's right. Yeah.
Good question. So upserts, why is it taking so long architecturally from a Postgres standpoint? Why is it being hard up until this point?
Good question. That's a few slides.
Okay.
Slide? Okay, so brief interlude before I answer that question. So, what if I can't wait till 2014? This is the actual example lifted directly from the documentation. That might not have been the best choice of color. Can people read that okay? Okay, I'll describe it anyway. This is a PLPGSQL function that you can call from SQL. So you can do a select, merge DB, calling the function. But you don't necessarily have to use a function stored in the database to do this. This is just the example happens to do that. So that's what I'm using. So we have this loop construct here. You're looping. First you do the update. You're checking if the update affected any rows. And if it did, you're done. If it didn't, you can do an insert. Potentially the insert can have a unique violation. And then you do nothing, and then you take it from the top. So that's kind of what we do. And there are some subtleties as well, like hopefully the unique violation here, potentially when you insert into this DB table, it could fire a trigger and the trigger could be the one that raised the unique constraint violation. So you have to be paranoid about that. So this is kind of crappy. That you can do this right now, but I'm trying to improve that. So hopefully I'll be successful. Slide. Okay, upsert and its thorny implementation details. Am I for time? Am I? I'm fine? Okay. So, what is the reason why it's taken so long to do upsert? I actually don't know is the answer, but I can tell you a little bit about the implementation details. So with upsert, what you're actually doing is you're locking values as in the integer 5, just generally in the abstract, on a certain index or unique index on a certain table, and you also need to lock the row that contains that value if there is a duplicate. So there was previously no way of locking values in Postgres, so I had to come up with that, or rather I am in the process of coming up with that.
Is that like column locking, effectively?
Pardon?
Locking values, is that like column locking?
No, it's like locking. So unique. Suppose we have a unique constraint on a pre-bit integer column. We need to lock like the integer 5. So no one can insert the integer 5. We're not talking about some particular row that we're locking that happens to contain the integer 5. We're talking about the integer 5 generally. So we need to say, hang on, don't insert any of those. I'm in the process of considering the question of whether I need to insert or update. And then, if there's a duplicate, we lock the value. Then we go and lock the row. There's a phase locking, and then we release the lock on the value and we're done. And then the transaction that originated all this can then safely go update that without there being any additional race conditions for them to worry about. So, because this uses, I suppose probably the main reason is people are slightly intimidated by the B-tree code. I mentioned earlier latching in B-tree indexes. This is pretty complicated, slightly intimidating perhaps. The way locks are acquired on pages in B-trees to ensure correct behavior. So maybe that's the reason why it's taken as long as it has. So unique constraints are always B-tree indexes under the hood. There was no way to lock values, and I've proposed a way of doing that. And the trick is to lock the value, to go lock the row, and to unlock the value, and then proceed. But to do it without race conditions, without deadlocks, and we're talking about low-level locks here that don't have a deadlock detector or anything like that. It's totally unacceptable for this stuff to deadlock because then the session just hangs forever. So it's quite subtle analyzing the problems involved with locking the values, locking the row, preventing there from being deadlock scenarios and things of that nature, or race conditions where you don't have an atomic insert or update occur. So the last phase, of course, we can insert the heap tuple. So we have two phases: checking and locking, and then insertion proper, or alternatively checking, realizing that there isn't, and then just locking. That's kind of how it works. Sort of the idea. So it's kind of a low-level concept from the MySQL syntax they provide. Hopefully more useful, but certainly at least solving the basic problem that a lot of people have. Omar, get up there.
So how does MySQL get away with it? Are they cheating, or are they?
I don't think they are. I think they just did it. I don't know. I guess they came up with. I actually tried. I tried to figure out what they do, but their source code is really hard to understand. So I don't know. But they do something anyway, and it more or less works. It's easy. But yeah, I mean, I think that the fact that we don't do it is just kind of weak. Yes?
It actually deadlocks like crazy all the time.
Really?
Yeah, for my eyes, and it's gonna lock the entire table.
Oh, yeah.
So that solves your deadlocking.
Yeah.
For InnoDB, it'll deadlocks happen all the time in InnoDB, but
Mhm.
it solves them pretty quickly, usually, until you get like, say, 500 current queries or something like that. At that point, something happens, and I don't get this in the CD cache anymore, and then it should also. But yeah, that's the first of that. There's deadlock, and it's serialized. It goes into a serialized pattern, and then resolve it.
Okay.
It's not.
Right, because, I mean, you get different behavior based on storage engine. My ISAM really only supports locking a table granularity. Well, I don't want to pick on MySQL because, or certainly not my ISAM because, I mean, it's not really what we're competing with at all. And,
Let's pick on Mongo instead.
okay.
It's always favorite.
Oh, you know, they have upstart, right? So, they have at least one thing we don't have. So, we're pretty much unique in not having some kind of upstart. So I kind of think that sucks. Okay, so I will take questions if you've got any additional questions. Do you?
It's on the last slide.
Okay, slide. Do you have any questions? Yes.
Do you put anything like PG Balancer in front of your database instances, or do you just try to partition?
Heroku?
Yeah.
Good question. We don't use PGMaster, or we certainly don't mandate its usage in Heroku because the tendencies for PGMaster to work effectively, it implies certain it implies the application developer being aware of it, which is not really our model. With Heroku, the idea is it just works. So you have to be aware of the fact that certain limited session state can sort of just change underneath you if you're using PGBouncer, which for an awful lot of applications is fine, but we're targeting a very general case. So certainly some of our customers do use it, but you don't get it automatically. Other customers will be using a connection pooler within Rails or things like that, and so they'll automatically have benefit of that. So the answer is no. We don't just use it. Making it possible for us to just use it and have no one care is an interesting problem and one that I thought of working on myself actually. But there are some sort of tricky details involved there, and it's kind of frustrating to have to work on something like that just to solve a very general case when if someone has a problem with that, we can just say, well, why don't you consider this, and then impose a few additional constraints on them, not too many, and just have them be happy with that. It seemingly hasn't been that compelling for us to solve it in the sort of general case.
So you don't have sort of like magical
No,
connection pooling.
nothing like that. I'm afraid you can use connection tools on Postgres.
Yeah.
If you're on our platform, but it doesn't just happen that magic, I'm afraid. Anyone else? Yes?
What are the pitfalls of using the array type? Sort of piggybacking on Tavis's question.
Okay.
So
The array type is very efficient in that there is a binary representation of the hood. It is indexable. You can there's many different operators that are indexable, so you can answer all kinds of arbitrary questions about things in arrays in your table. I guess some people might say the first problem is that you're violating the first normal form in using an array at all. I'm not one of those people, otherwise I probably wouldn't work for Heroku. But you know, this notion that that's not an atomic piece of data is considered questionable by some. So maybe that is one thing. Another might be that you know, potentially you could have if you had a very large array. I mean, for one thing, there's a hard limit on how big an array can be, and it's not terribly large. So certainly, you're not getting something like equivalent to a MongoDB collection or something like that. If you were to use arrays in that fashion, they're not suitable for that. But if you have, you know, the order of hundreds of thousands of distinct values, and it happens to suit the purpose to put those in the array column, by all means, that, you know, you can do that, and it works quite well, and it's quite a flexible approach. So I would encourage it if you think it makes sense. Anyone else? No?
What about, so Postgres is famous for having transactional DDL changes.
That's true, it is, yes.
How does that play into all the complexities of dealing with writing the code that you've been working on?
I suppose that Postgres is unusual in that everything, pretty much, is represented directly in catalogs, which are, for most purposes, ordinary tables. Now, of course, we do cache. We do have various caches that the catalogs use, so you're usually not actually querying a table, or, you know, along with all the overhead that implies. So I suppose the reason that we have transactional DDL is a natural extension of that. And it doesn't really play in at all, because DDL in Postgres typically requires an access exclusive block, which is the really bad one. It's the one that blocks everything. You know, that it doesn't. I mean, if you have DDL, then it's going to block everything out anyway. So it's not very difficult to reason about that. Since you asked, one issue that came up during the course of my recent work on insert underneath key, ignore, or lock for update, was that there might be a deadlock hazard implied by, you know, optimizing the order of, you know, indexes to lock. So that, like, if it was a serial column or something, you'd say, you know what, that probably is not going to have certificates, so I'll check out one of those. But someone suggested that might have deadlock hazards, and I encountered that, well, you know, in order to change that stuff, they're going to have to use DDL, and they're going to have to lock the whole table, so there won't be a deadlock hazard. This is the kind of back and forth we have. So I don't know that it is super relevant to what I'm currently doing, but anyone else? We done? Yes?
Does Postgres support column level locking?
No. What would you want it to?
Presumably less locking, right?
Well, I mean, locking is not necessarily a bad thing. You know, I mean, like I said, there's no way around locking. If those are the semantics that we, you know, as application developers have found to be useful, right? So locking is not necessarily a bad thing. I wouldn't like to think of it as a bad thing. We're locking the referenced rows in the foreign table, or doing insert, because we don't want those to go away. Because if they do during the transaction, then we'll get incorrect behavior probably. So those are the useful semantics we find. So locking is not necessarily a bad thing, although it's something to very much be aware of, perhaps, for certain people. Does that answer your question?
Sorry. We'll put you more over here.
Is that right? But I suppose maybe the answer is kind of yes, because you have that sort of select, the example of foreign keys, where you're not locking I mean, it's still actually a level lock, but it's, you know, it's sort of giving Postgres the introspection to say, hang on, I don't need to block people that just want to update. because I just making sure that the tuple proper doesn't go away. If it's another version of the tuple, well, that's fine. Because we're if you like, analyzing the way the blocks are acquired, making sure that we still support those useful semantics, so you don't have to worry about this stuff for the most part, and yet, making forms better. So you kind of think of those as not blocking the key column, I suppose. Anyone else?
I've got two more questions. One for the audience. How many people actually use Postgres?
That's a good one.
And for those who don't, what's the number one reason why they should love it?
Okay, what's the number one? I don't know. So a colleague of mine in the Department of Data, Daniel Farina, has described it as being the Emacs of databases. Maybe that puts everyone off, or maybe half the room, but I don't use Emacs myself. But I guess what he meant by that was it provides a lot of different facilities to solve an awful lot of diverse different problems, including the problems you don't even know about. Really the advantage of Postgres in essence is immense flexibility and extensibility. It is something that has been found to offer an awful lot of prepackaged solutions for an awful lot of situations. It performs pretty well as well, so, and it doesn't cost any money.
It's not owned by Oracle.
It's not owned by Oracle. Very good.
Wait, what was that again?
It's not owned by Oracle, which is the number one reason.
I hope that that's not the number one reason, but if it is,
You should ask our last speaker about that,
okay, who's the last speaker?
Brian Cantrell.
Okay. Okay. Are we any got a question or something? No? Okay, I think we're
Beers?
done. Thank you.
Thank you, Peter. Thanks you for hosting. Just a quick show of hands. How many people are interested in something afterwards? Beers, food? Okay. I'll make reservations shortly. Just a reminder, DevOps days, please come see me. Thank you, and see you next time.
When is DevOps Day?
25th and 26th of October.
Okay.